You'll probably hear the soldering iron buzzing in the background, the transformer in it, so you know things are going to get serious. I'm also back to the Moto G. I'm just mopping around between phones at the moment, trying to decide where I want to go. And if you're wondering why I keep going back to the Moto G, do you want to see why I keep going back to the Moto G? I think I should show you why I keep going back to the Moto G by demonstrating this tiny little circuit board here. Do you want a closer look at this little circuit board? One moment, please. Boom. That's why I like the Moto G. It gets in really, really close. Yeah, it's a fantastic camera on this phone. Right, back to the main event. And there lies the problem. You see, I could go for a super duper ultra flagship with 48 megapixel camera or more, but when it comes to the crunch, all these super high resolution cameras are really crap at focusing on things at close range, and as you can see here, things are at close range. That's a tricky bit. Anyway, I digress. I've not even started the video and I've digressed. That's a new one. Or is it really? So those of you who know me, and many of you will do this as well, when you strip out electronic stuff, you'll probably savage. Yes, you'll probably savage. This one looks a bit savaged. You'll probably salvage the lithium cells out them. Now, for those of you wondering about the safety of doing things like this, can I just point out that this rather fabulous lithium cell that came from Poundland of all places, it didn't cost £1, it cost £5, but that's all right for a 10 amp hour cell. It came complete with a product and lots of circuitry. That was featured in another video. The main thing is that it is a juicy 10 amp hour cell. I'd like to mention that it weighs 155 grams, of which just 3 grams is actual lithium. People seem to think it's just a solid slab of lithium. The reason these things go boom when they go up is because they store so much energy. And that's why when I take these out of products, the first thing I do is attach a couple of wires, put them into a Molex connector, which is shielded, so you know even if you've got metal in the vicinity, it's not going to short circuit against it. And then I put the Kapton tape over it to make them safe. Some of them have protection circuits, some of them don't. It doesn't really matter because when I charge them, I tend to use these little adapters. This is out of a standard power bank. It's a little module that comes out the end. This is the advantage that when you plug it into, say for instance, this unit here, then you've got 5-volt output. And because this is a big battery, and because this is one of these simple circuits that just remains active all the time, you can run very low current loads on it and they'll just run for ages. However, the advantage of this, using this Molex connector and a standard pinout, is you can also use it with little boards like this. This is the one we just had a close look at, is a classic TP4056 board. They're really cheap on eBay. They're charger boards that you stick the USB plug into, and then you can connect it to your battery pack and it will charge the battery pack. This one has the extra feature. It's got the DW01 protection and it's got the MOSFET, dual MOSFET. So this also has the protection for the battery that it can't be over discharged or overcharged. Not that that would happen with this circuit because this already has that protection sort of built into it. This one does have a little protection circuit built on board. It tends to be a bit of a hit and miss which one of the protection circuits is going to trip in first. So I thought I'd show you applications for these lithium cells. A particular application I like, and that is to drive strings of cheapo LED lights directly from the lithium cell without any sort of USB booster. So here's what I'm going to do. I have a little rechargeable lithium ion battery. It claims 1000 milliamp hour. I doubt it. And what I'm going to do is I'm going to stick a couple of leads onto it. And this gives me an opportunity to bring in another of the tools I've featured before, but I'll feature it again. This is a terminal crimping tool. I got this from Rapid Electronics. I got all these connectors from Rapid Electronics, now widely available on eBay, but that's where I got the connectors and still get them. This is the correct tool for actually crimping these terminals, and it's quite expensive, but it's worth its weight in gold. It also takes a bit of getting used to this tool before you finally click with it, but you know what? Once you've got used to it, it becomes quite quick to actually terminate the crimp. So what I'm doing here is I'm putting the wire into the end of the crimp, just pushing it in, just a wee bit of the insulation in, and it crimps down, ratchet action, so it won't release until it's fully crimped, and then it opens again, and that has firmly crimped onto that connector to the point it's not going to pull out. Some of the cheapy eBay crimping tools are very, very random, and the crimp you get isn't always quite as secure as you'd like. So I'm going to crimp the negative connection now in the same way. I have to say, when I first used this tool, I hated it because it takes a while to get used to it, but once you're used to it, you can fly through the crimps, particularly if you're making a lot of stuff. This has been used to make the wiring looms for so many props, for television and film, and for promotions like Aftershock promotions, the wiring harnesses for the strange machines that were made for those promotions. It's just, I well and truly get my money's worth out of this from the sheer amount of use it got. So the Molex connector, what I meant to do before I started this video was get some of the bigger Molex connectors to show this, but not to worry. Most of them have a number 1 on pin number 1. In this case, if you're looking at this Molex connector with the two little clip bits that actually latch the contact in, the one closest to you when they're at the left, I put the positive into, because usually most of my applications are common positive with the switch negatives in the sort of LED controllers. And if I slide this one in, you might hear a very slight click. I'll just lift it up here. Did you hear the click? That was it clicking in, and it's not going to come out now. The only way you can get that out is to push those little prongs down and pull it out, but that tends to mash the connection in the process. Let us connect this to this battery. So what I'm going to do, I'm going to tin these leads with a little bit of juicy lead-based solder. I'm going to crop them down just a little tiny bit because the plastic sleeving on the cable, the sheath, has slid back a bit with the heat. I'm going to put some solder onto the contacts and then to this battery. Now, this is a sort of Nokia-style knockoff battery. Does it even have a number on it? No, it doesn't have the number, not to worry, but it's a generic, very common style of battery. And some of the circuit boards for protection, these little gold pads here, some of them are real protection and some of them don't have the overload protection or overcharge protection. Something worth checking out. Not so critical if you're charging it on one of these little modules that I've got here. So I'm going to solder onto those gold pads. Just run some solder on, and then getting the polarity right, which is positive over there, I'm going to solder the positive lead in there by flowing them together again. Melting the plastic a little bit, but I'm not really too bothered about that. And the negative, they're actually marked positive and negative here. I suppose it would make sense to check that. I will check it. Let's check it right now. So I'll bring in the meter. It's already set to 20 volts, that's fine. Some of you ask, why do I use a manual range meter? I just like the big display in this one. That's the main reason I use it. I've got auto range meters. The polarity is correct. It says 4 volts. It's almost fully charged. If it was showing negative, when I put the positive, the red in the positive and the black in the negative, then it would be the wrong polarity, but that is the correct polarity. Now comes the item that I'm going to connect it, which is this string of LED fair lights from Poundland. This is part of their Christmas stock, and as a special treat this year, the ones that say coloured LEDs in the box are actually going to be coloured this year. You can tell because you can see the phosphors. You can see like the clear for the blue, the green phosphor for the green, the yellow phosphor for the yellows, and the red phosphor for the red, because they're all using sort of blue chips. Last year, their coloured sets were all cold white, which was not very colourful. I mean, technically speaking, that is a colour, but it was a bit of a disappointment. So what I'm going to do with these, I'm going to put the same connector on, and there lies the first hurdle. How am I going to connect it to those if it's the same type of connector? Well, I'm going to be putting a resistor in between. And the reason I tend to use these connectors on the strings of lights is because it's much easier crimping them on than it is trying to solder and sleeve them. So I'm going to strip these with this set of Unior cable strippers. Some of you ask where I get them. To be honest, I think this came from Bill's Tool Store in Glasgow. Quite hard to get. There are other strippers you can get that are a lot easier. I use those ones just because I prefer them, to be honest, the manual ones. They offer good control. Some of the automatic ones have sort of strange behaviour with thinner cables. They'll just strip the cables completely, including the copper. So I'm going to clamp that down gently. Not too much because I want to slide these connections in, noting that I don't know the polarity at this point in time. It doesn't really matter. I shall sort that out afterwards. So I'm going to fumble that in, and I really am fumbling that in. There it goes. I shall crimp it. Have I crimped it too far? No, it's fine. And the next crimp, I could have zoomed down a bit for this, but I know that sort of annoys some people. And let's get the other connection in. I do intend to move to another phone. I prefer phones for recording my videos because it's just the ideal device for recording YouTube videos. Mainly because it's basically a Google device. So this gets put out the way now. And I don't know the polarity, so I'm going to get a lithium button cell. And I'm going to stick these on either side lithium button cell. They have lit up. That means that this connection is the positive and will go into the same position in this housing. If the wiring is too flimsy to allow it to click in, it has clicked in, you can poke it in with a thin screwdriver. Right. Now, if I was to connect these lights directly to the output of a lithium cell, particularly a fairly chunky one like this, it would pump a lot of current through them. It would not be a good result. So I'm going to have to put a resistor in line. Let's get rid of this lithium button cell, which contains approximately 0.1 gram of lithium. This is a non-rechargeable one. The non-rechargeable ones contain about the same amount of lithium as the rechargeable ones. Is that about right? Let's see. I'm not sure. I'd have to check that up. But this one can be charged hundreds of times. It just seems that, you know, yeah, it would be a good idea if they were all rechargeable. Right, what we're going to do, I'm going to bring in the helping hands, and this is where I will zoom up a little bit because it's going to need a little bit more detail to see what I'm doing here. I'm going to make a back-to-back connector. I'm going to put a resistor in now. The choice of resistor will determine the current. It depends, literally, how bright you want the LEDs, how long you want them to run for. If you run a string of LEDs like this at 20 milliamps, and keep in mind again that if you were using this to drive the LEDs with some resistors and it put out a constant 5 volts, the LEDs would just stay at the same intensity all the time until the battery ran flat. If you're just using a resistor with a lithium cell, the voltage goes down from about 4.2 volts down to about 3 volts. And at that point, many of the protection circuits kick in. In this case, there's no protection circuit, but even before it's anywhere near being over discharged, these LEDs will pretty much have stopped conducting because they don't really pass much current below about, say, 2.6 volts. So depending on the resistor, you can choose how long you want them to run at what sort of intensity. And if it's just in the house, if it's a bit of ambient splash of colour, I would say 100 ohm is absolutely fine. So let's assemble this. If you look at my helping hand here, you'll see I've got one of these terminals actually stuck down with double-sided tape, and it's marked red and black. That is purely to remind me the polarity of these when I'm terminating onto them. So I'm going to tin that lead by just flowing a bit of solder onto it. I'm going to tin both. No, I'm going to tin just one lead. That's a good idea. I've been experimenting and working out the best way to do this. I'm going to get the 100 ohm resistor. That's brown, black, brown, 101, 10 and 10 is 100 ohms. And I'm going to crop the lead just enough that it can solder after being tinned onto that connection, but not right hard butting up against it because I don't want to actually put stress on the end of the resistor lead. So I'm going to put some solder in that. I'm going to touch it onto there. This is when it would have been quite good to bring it up closer, but I didn't. And I'm going to flow that on. Next, I'm going to crop the other end of the resistor and keep the leads because you're going to need one piece of this lead. And the other side of the connector, I'm going to actually, just to make it easier to hold, it is actually going to go upside down versus the other one because we want both the positive sides connected together and both the negative sides. In this case, the positive side, I think it's positive side, yes it is going via the 100 ohm resistor. So I shall just make sure I'm not doing anything weird here. This is going to be, let's see, yeah. That should be fine. I shall put a red dot in this just a reminder. It really helps. A little red dot on the side. It doesn't take much time. And I'm going to plug this into one of the connectors, not because I need an electrical connection. There's no contacts in that, but just to hold it. And I'm going to flow some solder onto that resistor. And I'm going to flow some solder onto that lead. And then I'm going to put them together and reflow them. Slight tail of solder there, but I'm not too bothered. And then I'm going to pull this part of the connector off. I'm just going to trim that little sharp bit because I will be putting a heat shrink over it and we don't want sharp bits. Okay. Now we're going to take one of the crop leads and the other two connectors, we're going to bridge them like this. I'm going to put it in, see where I have to cut it, trim it down, I think round about there, poke it down onto that, and then solder that in. So that's just sitting down in the grooves here on the contact. It means that it holds itself in place. It's just a wire link from one side to other of the negative connection. So I'm going to solder one side and then the other side. Perfect. That is now a link with a 100 ohm resistor in line with it. Now, to make it stronger, because it's not very strong and it's also a bit bare and exposed, I'm going to put a bit of heat shrink sleeving across it. So I'm going to put a bit of sleeving across like this. I'm going to try it for size, crop that down with a pair of scissors. This is actually adhesive lined heat shrink. It doesn't need to be adhesive lined, it's just what I had in the correct size. I shall crop just a wee tiny bit more off that because we don't want it too long, although we can crop it down afterwards. And once again, I'm going to plug this in here just to hold it. And I'm going to get a hot melt glue gun and I'm going to squirt a bit of glue onto that resistor. Maybe a bit too much glue, but that's all right. And turn it over and put a little drop the other side as well, or just let that just sink through. That's looking pretty good. Looking pretty good indeed. I shall just turn this off because I don't need the hot melt glue gun on anymore. And I'll put it down somewhere that I don't kick it. So now that hot melt glue, it doesn't really matter what sort of shape it takes a moment because I'm going to put this sleeve over and it's going to get messed up, that hot melt glue. It doesn't really matter. And holding it at finger safe distance, I'm going to bring in the little hot air gun and I'm going to shrink this sleeving. I'm going to start at one end, shrink it on, and then basically just work my way across, and it will shrink down and that hot melt glue will squish in to fill that whole void in there. And once it's cooled down, that will give us a nice solid core in the middle. Am I still in shot? Yes, I am. This is good. This is unusually good for me. Okie dokie. So now we've made our little thing. Let's let it cool. So I'm just going to leave it to cool for a moment. The hot melt glue has cooled and we're ready to try this out. So I'm going to plug this into the connector. It doesn't matter which way around it goes. All we're doing is adding a 100 ohm resistor in series. I connect into the battery pack and the LEDs light up. Now, to measure how much current these are drawing, there's an interesting thing you can do. We could stick a clamp meter around it. Let's do that. Hold on. Let's get the dinky little meter here. and I shall pause. Because you can affect the reading by changing the sort of environment around it, the magnetic fields around this when it's in DC mode. What I'm going to do is I'm going to select the DC mode, I'm going to cancel it out, and then carefully, without doing too much here, turn the lights on, and it says about 15 milliamps. Okay, but we can get a more accurate reading than that without sticking a meter in series. Ideally, to get current reading, you'd normally just stick a meter in series and measure the current, but in this case, because there's such a tiny voltage being dropped, the resistance of the meter itself is actually going to be a factor. It's going to limit the current. So we'll bring in a meter, and instead of setting it to the current range, we'll set it to the voltage range. I don't think it's going to be terribly high. Let's set it to 2 volts. And we'll measure the voltage across the resistor. So I'm going to put a connection in here, and a connection in here. And the voltage being dropped across the resistor is, once I get my probes into the recessed connectors, shall we say 1.4 volts? Let's say 1.4 volts. Okay. And we'll do the maths. The mathematics. So that 1.4 volts, to measure the current, 1.4 volts was measured, 1.4 volts was measured across the resistor. Divide that by the value of the resistor, 100 ohms, gives 14 milliamps through those LEDs. If you wanted more current, if you wanted them to be brighter, you could use a lower value resistor. You could go all the way down to 10 ohms. And even at 10 ohms with the sort of standard lithium cell and the standard gallium nitride LEDs, you'd be able to go down to 10 ohms without deviating from using a quarter watt resistor. They'd be absolutely fine for dissipation at that level. And the current would be significantly higher. But it all depends what you want. You can just choose the resistor you use. Or you can do what I do. You can make a little batch of these up with different value resistors. And then because they're clear, you can see the value, or you can write it on it. And then you can just choose what intensity you want by changing the resistor. So there is another test I'd like to do. Oh, I'd like to mention, with the LEDs running at this level, this is fine. This is a sort of, well, let me show you. Let me take the exposure off, and this is going to exaggerate horribly, isn't it? Yes, it is. It's going to exaggerate, but they are pretty bright. However, I want to do another test here, and that is, I'm going to short this battery pack out. Not in a bad way. You see, this contains a DW01 chip, and if you see the LEDs are lit at the moment, if I use 2 1 ohm resistors in parallel to give half an ohm, that's effectively going to give somewhere between, depending on the battery, internal impedance, it's going to give, and the MOSFETs that are used in the protection, it's going to give quite a high current of anywhere between, say, 4 amps to 8 amps. So when I bridge this across, did you see how the LEDs went out and stayed out? To get them to light again, I'm going to have to unplug that and plug it in again, and they'll reset again. That means there definitely is a protection chip in there. Let me explain how that works. If I bring in this schematic of the protection circuit, so this is the classic DW01 chip. On this case, it's this tiny little chip here, and it interfaces with MOSFETs, and that chip there is 2 MOSFETs in one package. It's a really common arrangement for the protection. One of the MOSFETs is energized for charging, one is energized for discharging. It's just the way it works. The MOSFETs will be chosen depending on the expected current. So if you've got something like a little low current battery pack, like this for instance, it will be a tiny little MOSFET, even smaller than that one probably. If, however, you have a big fat battery packet that can deliver several amps continuously, you'll have bigger MOSFETs, or quite often a row of them in parallel. And the reason for that is that every MOSFET has an equivalent resistance when it's on. And let's just draw that in. So let's just draw it as a resistor across here. So I'll just call that MOSFET resistance. And okay. And as the current goes up in this circuit, the voltage measured across this point and this point, basically this end's connected to ground, and this end is being sensed via this 1K resistor to current sense, which is, so it's measuring the voltage drop across these MOSFETs. If it's a slight overload, it will just cut out momentarily and come back in. If it's a significant overload like I put on, it will turn the output off and it will then monitor for the load being removed and then applied again. Or in the case of some of the power banks where it can detect the other circuitry, you may actually have to give it a wee boost, give it a wee charge before it will actually reset again. And that is purely to protect these MOSFETs from damage, and also it means it can actually protect the lithium cell from that overload as well. The reason for this 1K resistor, it's always 1K, just like that one is always 100 ohm. The reason for these is that the 1K resistor is purely for chip protection. It doesn't affect the voltage reading at all. It just means that if the polarity is connected wrong, it's going to give this chip a fighting chance of, protection against that. It just basically limits the current flow in the event of fault conditions. In the case of this 100 ohm resistor and this 100 nanofarad capacitor, they just form a filter across the battery, so the chip gets a nice stable reading from the battery. Even under spiky pulsing current loads, it gets a nice stable reading, so it can actually monitor the voltage across that and determine when to turn these MOSFETs off when it's either overcharging or over discharging. Other things that are worthy of note are that if you think about it, this splendid 10 amp hour cell, if these are drawing 15 milliamps, even although as the voltage goes down, that current will actually go down as well, because the voltage drop is such that the voltage across the resistor will be lower, and therefore the current through the LEDs will gradually get lower. So these won't stay at the same intensity and then sort of just go out at the end. They'll just gradually fade down till you say, time to charge the battery. But by that time, the battery will still have a decent amount of charge in it. However, if it was 15 milliamps all the way, keep in mind that this is a 10,000 milliamp hour cell. So if we did run those LEDs off that, divided by the 15 milliamps they're actually drawing, they'd run for 666 hours. Ooh, mark of the beast, etc. Divide that by 24. That's going to run for 27 days, but that would be at that same current all the time. Because it's lowering down over time, this would actually keep these lights lit 24/7 for well over a month. And then, it wouldn't even be fully discharged at that point, but you could just top it up as needed. So you can see that even like this, if this was 1000 milliamp hour, let's pretend its actual value is probably closer to 600 milliamp hour. Let's say worst case 500 milliamp hour. Let's bring the calculator in again. How long is it going to run those? So 500 milliamp hour divided by the 15 that's actually running, it's going to run it for well over a day. And quite frankly, it would be several days that it would actually run, because it was reducing in current all the way. So that's it. The only thing I need to do now is finish the task of this battery here by putting a bit of Kapton tape over the contacts in the end, just so it doesn't get pushed against anything and shorted out. So I shall do that right now. I shall cut a little bit. I shall fold the leads to the side. Actually, I'll put them out the long way. That's a good idea. I shall put the tape over there. And I'll probably cut another bit as well. And if I was going to extremes, I might go to extremes. I'd wrap it round the side as well to secure those bits of tape in place, because, well, the more insulation, the better. I shall do that. I shall put the tape on like this and wrap it round, and that little salvaged cell, that little cell that I think I used this in one of the GPS trackers for my mum when she was sinking into Alzheimer's. This must be one of the batteries out of that. We kept lots and lots of them, so we always had one fully charged and ready to just pop into the unit if it sent the message saying the battery was low, or indeed every morning. But there we go. And when it does run flat, you just unplug it and you plug it into one of these little modules and charge up again from a standard USB charger. So that's what you can do with these lithium cells. Just make sure that they are used where they can't be punctured or anything like that, and that everything's well taped over and reinforced, and they're not kiddie toys, etc., etc. Disclaimer. But just fine for running LEDs for your ambient pleasurement. So there we go. A simple project that has good results.